Understanding complicated systems with scientific basis. 400 AD. In the aftermath of the Rome Empire falling apart, all the knowledge was lost. Nobody could read. People couldn't communicate with others. Average person never went more than 12 to 15 miles away from where they were born. 1085. First European Christian conquest, in Toledo, Spain. Within that city was a library with more books than all Europe combined. They rediscovered Aristotle, Plato, logic, transitivity, syllogism, etc. Thomas Aquinas. God cannot sin. God cannot make a copy of himself. Even God cannot make a triangle with more than 180 degrees. They realize they could reconstruct events by looking at overlapping fragments, using facts, observational data, and putting them together. Reductionism. If you want to understand a complex system, you break it down into its component parts. And when you understand the individual parts, you can understand the complex system. Linearity of a DVD. Once you know how the individual's parts work, you add them together, and they'll increase their complexity in a linear manner and you will produce the whole complex system. As consequence, if you know the starting state of a system, you will have 100% predictability of how the system will look like in the future. Also, if you know the complex system, you can figure out the starting state. Extrapolate. You can see the answer to something in different iterations, using the same rules over and over again. Where you can know the answer to something without having to go through all the calculations. Blueprints. All of this requires already a notion of what the outcome is supposed to be, when you add these linear additive rules. Variability. Different values for something that winds up averaging something you want to measure. So, what is variability about? It's noise, it's junk in the system. And it is stuff you want to get rid of. Noise equals instrument error. And the best way to avoid this noise is to become more reductive. The closer you look to a phenomenon, the closer you will be to seeing what actually going on. As a result, variability should disappear. The closer we look to the component parts, the closer we will see how the system really works, to see what truly is going on without the noise, because all the noise is discrepancy. The biology of the body. How the body works - how organs work - how cell work - how molecules work - you understand them - add them together equals you know how the body works. Problems in biological systems. E.g. 1. Hubel and Wiesel, 50s to 60s. How the cortex works, of how you extracted information from the visual world around you. They showed that you could find individual cells in the retina that corresponded to individual neurons in the simplest part of the visual cortex. Between them, you had point-for-point reductive relationships. If you stimulate the retinal cell on the right, which associated neuron in the left part of the cortex would get excited and have an action potential. If you shift your electrode a little bit and stimulate the one right next to the right, the neuron next to the left is going to get stimulated. In other words, if you know the starting state, which receptors in the eye have been stimulated, you have 100% predictability of which neurons on the left appear. So, the first layer of the cortex have this one-to-one correspondence. Each of these neurons could recognize a dot. Take those individual neuron component parts, put them together, and you will know what just hit the eye. Then, the second layer of the cortex. It only gets activated when you do the same process as the first layer repeatedly, until you form a line. Only if you first stimulate this photoreceptor, followed by one another, which is light moving in a straight line in one direction. So, that part of the cortex could extract the information from the first layer, and put them together, and get different sorts of information. Thus, you would have another neuron coding for an angle that was slightly different, different parts of the cortex, of the visual system, etc. So, each neuron knows about a curve and one curve only. First layer equals recognize dots. Second layer equals recognize straight lines. Auditory cortex does the same. One cochlear hair cell recognizes a single note, up to chord, and so on. Until you find neurons that were specialized in complex sensory information. They called them grandmother neurons. With enough layers, you would get neurons that responded to only one complex thing, until you get neurons that only recognized your grandmother. Grandmother neuron. They exist relatively. A single neuron that will respond to only one type of face. E.g. some people recorded the very upper layers of visual cortex in monkey brains, where only one neuron would respond only to a certain human face. And also, they found a neuron that only would respond to a picture of Jennifer Aniston, which would respond to her photograph, at different angles, caricature, etc. And even more, a neuron that responds to a picture of Sydney Opera House. They called them sparse coding. where you only need few neurons to recognize fancy things. But in really, you don't have grandmother neurons. Because you will need tons and tons of neuron on your brain, to do face recognition, in a point-for-point reductive manner. Non-reductive approach. They looked at neural networks. Because complex information is coded in patterns of activation across thousands of neurons forming patterns. You can't recognize faces by using reductive component partner biology. Bifurcating system. It's scale-free. If you look at branching patterns, you can't tell which one you're looking at. And the most important things in our bodies are bifurcating systems. All the branch points on neurons are bifurcating. Bifurcating dendritic trees of neurons. Are dendritic tress. When they get more complex, they increase their arborization. The circulatory system. It's a tree bifurcating into little capillaries at the end. The pulmonary system is the same. But how the body make bifurcating systems? Because there's not enough genes in the genome that exist to code for it. You can't code for an organism that covers different scales from one cell to another. So you can't code for it in a point-for-point reductive way, where the components are individual genes. Not enough neurons, and not enough genes. Randomness. Brownian motion. Molecules vibrating, and when cells split, the distribution of mitochondria is unequal. E.g. identical twins. At fertilized egg stage. Even they have different mitochondria when they split. Or, the same happens with transposons, genes humping around. Yvonne Chase. Emergence of dominance. 10 fish. Each has a tank of their own. Then, you get every possible pairing of fish to fight, and see which one is dominant. At the end, you have your dominance hierarchy. But once you put them all together, there's no resemblance whatsoever. The pairing dominance outcomes don't predict the dominance hierarchy when they're all together. All because of chance. In biological systems, reductive systems break down, because there's not enough pieces to explain complex function. The most interesting stuff can't be regulated in a reductive way. Chaotic systems. When you have a system that's not reductive, where there's nonlinear, non-additivity. Reductive approaches can be used to fix clocks, reductive approaches can't be used to understand why clouds don't rain. Nonlinear systems, non-additive systems. You break something down to its component parts, put them back together, but they've added up differently. Determinist and periodic system. 1, 2, 3, 4, 5. Now you can predict which is going to be the step number 50, without doing the steps in between. Determinist and aperiodic system. You don't see periodicity, patterns that repeat. To solve it, you need to go stepwise and apply the rule over and over again. Non-determinism system. There's randomness in it. There's no set of rules applied over and over again. Nonlinear system. A system where even knowing the starting state, you can't know the outcome, without having to go through every single calculation. As a result, systems of nonlinear aperiodicity wind up producing chaotic systems. Explains the Lorentzian water wheel. Then, somewhere in the doubling process, it becomes a nonlinear chaotic system. As you increase the force in the system, it stops the perfect periodic doubling of the components and shift to a chaotic pattern, which generate a pattern that never repeats. So, even knowing the beginning, you can't predict the outcome. Structured, reductive, linear systems - increase the force on it equals it becomes chaotic, with no predictability. York. When any system like this begins to have 3 components before the pattern repeats, it's about to become chaotic. Before this, scientists stopped studying these systems when they found noise and variability. Because they thought the system had errors. And also, they thought that the best systems work in reductive periodic systems, where they just artificially excluded their ability to see what's actually happening. Implications. Linear systems like this have attractors. Even if you mess with it, the system will equilibrate and hoe back to where it was. In chaotic systems, when the system becomes chaotic, it forms the butterfly wing pattern. It's not settling down into a repeating pattern. It never touches the starting point, but it's being pulled by it, which is a strange attractor. As a result, the variability is not noise, it is the phenomenon. In complex systems, there's no answer as to what you're supposed to be observing, and everything else is noise. Noise is the system itself. And if you look even closer and closer, you will see that it never gets to the same exact spot again, they're differing by 1 decimal place. Also, the consequences of this tiny little difference gets amplified. Called the butterfly effect. The fact that a butterfly flaps its wings in Korea, it might change the weather system in Indiana. As a result, a gazillion decimal places out there, and they differ. This isn't noise in the system, this isn't variability, This is intrinsic to the system. And the fact that it will expand, it makes it unpredictable because of these butterfly effects. Also, strange attractor. Not only it has no predictability. The closer the look, you will see the same degree of noise variability. But most important, in chaotic systems, there's no real answer. The notion that the solution is at the center, is a fabrication of the data oscillating around there. Also, is scale-free. It doesn't matter how closely you're looking at it, there's always variability. So, the notion of reductionism, that the closer you look equals variability goes away, is false in a scale-free chaotic system, because the amount of noise will always remain the same, because it's not noise, it is the system. What a fractal is a complex visual pattern, that it's scale-free. His appearance is the same, no matter how closely you look at. His complexity, variability, etc. remains proportionally constant. A fractal is a fraction of a dimension. Bifurcating systems are fractals. Thus, his variability isn't noise variability, it's what the system is actually about. So, all these physiological systems are fractals, which have equivalent scales of complexity, at vastly different scales of magnification. All of these solve the problem of, there's not enough genes in there, due to the notion of fractal genes. Genes that give instructions that are independent of scale. Variability isn't noise, is the system. E.g., in biology, study the data of scientific literature at different scales of reductionism, and see their variability. Like the effects of testosterone in behavior. They looked at every single paper available, and then measure how variable were the data in the studies. They come out with a coefficient of variation, which is, how much variability to their total size. Then, he measured the mean and error bar in every single figure in the paper. The average coefficient of variation was 18%. At the organismal level. Organ system. Single organ. Multicellular. Single cell. The variability didn't decrease, it remained fairly constant. The data don't get cleaner, because it's a fractal system. Variability is the system, rather than discrepancy from the system. Is classical reductionism good for anything? It's very good in biology. If you're not very precise, very picky. E.g., a novel viral disease. You try to create a vaccine for it. Then you distribute it to people. And you see what Jonas Salk saw. It prevented polio. But 1 in 560 kids, it would get a worst case of polio. Where's the reductionism useful? On the average, it's a lot better that kids got this vaccine than they didn't get the vaccine. Or, if you want to know the weather 3 years from now, you can only know if it's going to be warmer, colder, etc. On average, it's better to have reductionism. Nonetheless, if you want to really understand the system, don't use reductionism. Because in interesting complex systems, there's not the answer, or the solution. Thus, the people outside that don't match the perfect one, they don't deviate the real answer. The variation is what it's supposed to be.